So good afternoon, everyone. My name is Francesco Petruccione. I'm the interim director of NITheCS, and I'm happy to welcome you to the July mini-school. Yeah? And today I'm super happy to introduce to you Jan Joel David. Jan is a upcoming superstar of quantum computing in South Africa. He's almost ready to submit his master thesis, and together with Jan, we had already fun a few times in offering this crash course introduction to quantum computing in a hands-on way. Yeah, earlier this year, we offered a similar version of what you get to hear this month in a course to the CSIR. Yeah, we stripped it down a little bit. Jan will just present you the practical side of accessing quantum computers in the cloud with some nice examples. Yeah. So and chatting to Jan before the mini-school starts, we agree that we will post the Jupyter notebooks that Jan will use this afternoon on the NITheCS website, so that if you are happy to play around on your own, you will be able to do so. And in some of the notebooks, Jan has introduced also some exercises to induce you to play around a little bit more. Yeah. But Jan, we don't have much time, and people are here to listen to you and not to me. You're most than welcome to start sharing your screen and start the first of the 4 lectures that we're planning for July. Thank you very much, Jan, for agreeing to do this mini-school. We really appreciate your assistance and your help. Thank you.
Thank you, Prof. Thank you. Good afternoon to everyone that's here. I'd like to welcome you to the July mini-school as well. As Prof just said, my name is Ian Joel David. I'm actually a student of Professor Petruccione as well as Professor Sinaisky, and I'm going to be giving you the mini-school on a practical introduction to quantum computing with Qiskit. So the outline for the mini-school was actually sent to you with the Zoom link. So it's open here, and I'm not really going to go through it because I'm sure you had a chance to read it. But just as an overview statement, I think I just want to say that over the next 4 weeks, I'll be introducing you to the practical tools that you need to do to program quantum computers and do simulations of quantum computers and quantum algorithms using Qiskit, which is a Python package. I'm going to assume some stuff. So I'm going to assume that you are familiar with the basics, at least on the theoretical side of quantum computing. And if you're not, there's a very nice mini-school that's available on the NITheCS YouTube channel by Dr. I think it's Professor now, Daniel K. Park. And you can go through that, as well as the many other very nice quantum computing introductory courses that are available online. Just some interesting resources you might want to look into. I will also put up this outline. I'll share it with Prof, and maybe he can put it up on the NITheCS website. It might be available there, but some resources that you might want to look into. There's the standard quantum computing textbook that we're all aware of, and that's the Quantum Computing and Quantum Information by Nielsen and Chuang. It's the go-to textbook. And if you really want to learn, everything from the basics to the advanced stuff in quantum computing, I think this is the go-to book. Some other good resources that you can look into if you haven't had any experience with quantum computing would be this resource here, which is an introduction to quantum computing without the physics. And this is quite a nice paper. It is quite rigorous, and I think maybe if you haven't been too familiar with quantum computers, or doing the theoretical side, or even in terms of just programming quantum computers, whatever you have as a background, this will serve as a good resource to you going forward. And there's also these very nice lecture notes by Ronald de Wolf, which I refer to on some occasions in preparing some of these these notes as well as these Jupyter notebooks. So these are 3 resources I think you can look into if you are interested in doing more reading about quantum computing. So today, the plan will be as follows. I just want to introduce you to Qiskit, which is a Python package that will allow you to do simulations of quantum circuits, implement quantum algorithms, and also access the IBM quantum computers in the cloud. If you haven't installed Python packages before, then you can go to the Qiskit website, or you can just type qiskit.org into Google and you'll get there. And having a look at the installation section of the documentation, it will advise you very nicely how to install Qiskit. I can actually show you very quickly the Qiskit installation part of the documentation. So if you just type Qiskit installation into Google, you should get this this web page, and it will walk you through installing Qiskit, everything from using Anaconda, creating a separate Qiskit environment, and then installing the necessary parts of Qiskit into that environment so that you may use it with either Jupyter Lab or Jupyter Notebook. So I think I can add this link as well to the outline, and you can come here and then follow the installation for yourself. But for today, I'm just going to be working with Qiskit in Visual Studio Code. This is my current preferred IDE, but you can feel free to use whatever you want to use. Just to save some bandwidth, I'm going to switch off my video. Okay, so first things first, I already have a Conda environment created, and I've called it Qiskit ENV. And the goal would be to then install Qiskit. So I already have Qiskit installed, but if you don't, this is the way you can do it within a Jupyter Notebook by just adding an exclamation mark. It's going to run this terminal command, and you just do pip install Qiskit and pip install Qiskit visualization. This is for plotting some circuits and other plots that you might need to look at the count numbers or even the Bloch sphere, which we'll get to in a moment. So once you've installed Qiskit and the visualization tools, we can begin with getting started with using Qiskit. So the first question is, what is Qiskit? As I've said already, it's an open source software development kit for Python, which allows you to work with the Open Quantum Assembly language, as well as the IBM Q quantum processors in the cloud. Qiskit has many tools that will allow you to do quantum computing very easily. It will allow you to do things like create and plot circuits, to run those circuits using various simulators, to run those circuits on real hardware. It'll allow you to do things such as state tomographies, and it even has a lot of built-in methods for doing things like some quantum machine learning, as well as quantum chemistry. But for today, we're just going to look at a lot of the basics of Qiskit, the functions you want to import from Qiskit, and just how to do some basic computations within quantum computing. Okay, so we want to use some built-in functions from Qiskit to compile our first quantum circuit and then run it. I will start off by running it on a simulator, purely because it's easier for demonstration purposes, but maybe in future weeks, I will show you how to run something on a real device. But for today, it's very simple. We're just going to run a very basic quantum circuit. So we're going to need some. We're going to need a few packages. Sorry, I'm actually hearing a little bit of feedback. I don't know if someone's mic is unmuted.
Check that for you, Ian.
Okay, so we're going to need to import a couple of packages and some functions from those packages so that we can construct a quantum circuit. Just as a very brief, outline of what a quantum circuit is, it is basically the diagram that we use to represent the unitary operators that evolve our quantum state in quantum computing. And we're going to create some of these quantum circuits and run them using Qiskit. So the first thing we need is NumPy. And then we need a couple of functions from Qiskit, the quantum circuit, the classical register, and the quantum register. Now, the classical register is going to be a collection of bits in which you're going to store the information you obtain once you measure your quantum bit. And the quantum register is just a collection of quantum bits or qubits. So when we create a quantum register, we're going to populate it with as many qubits as we want. And then if we're going to measure that qubit and we need a place to store that information from the measurement, we need to store it in a classical bit. So usually we have the same number of classical bits as we do qubits. So once we've imported these functions, we also need the execute function that's going to run our quantum circuit. We can create a quantum register Q, and the parameter 1 is just telling us that there's just one qubit in this register. And we also create a classical register with just one classical bit, which is going to allow us to store the information that we obtain when we measure the qubit. Then we create the quantum circuit object. This is going to be the object we use to add gates to the circuit, which I'll show you below. And this quantum circuit comprises of both the quantum register and the classical register, and it'll allow you to perform operations on the qubits in the quantum register, and then it'll allow you to store the information that you obtain from measurement in this classical register. So, of course, in the notebook itself, you'll find explanations of each of these functions, and it's fairly self-contained. So as you follow it, you'll be able to follow the whole lecture. So the first very simple circuit we want to look at will be to just do a NOT operation, but for qubits. So if you've done any classical computing or even any logic or anything like that in mathematics, you'll know that you have something like a NOT operation. That is, if you have a classical bit, say 0, and you apply the NOT operation to it, it makes it 1. And if you have a classical bit 1 and you apply the NOT operation, you get 0. So we want to do a quantum circuit that will have the equivalent of this, but in quantum computing. So we know that in quantum computing, the state of our single qubit is represented by a Ket vector. And the computational basis that we will use will be the two Ket vectors, 0 and 1, as you can see here. So our simple NOT gate that we want to use should take this, the computational basis state 0 and map it to 1. And if you have the state 1 and you apply the NOT gate to it, you should get the state 0. And I'll show you later on what these states look like as vectors, but for now you can just think of these as column vectors. And the idea would be to just apply a gate, which is just a matrix, to that column vector, and you get a new vector. So we're going to be doing all of this, but using Quizkit. This is stuff that you should be familiar with if you've done an introductory course in quantum computing. Okay, so the first thing we want to do is we have our quantum circuit object that we've created. And when we create a quantum register, it initializes the state of all the qubits in that register to the state 0, so this Ket 0. So every qubit in my quantum register is initially in the state 0 like that. And if we want to apply the NOT operation to it, what we will do is we will say QC.x, where x is just a gate, which corresponds to the Pauli X matrix, or the sigma 1 matrix, if you know that notation as well. And this X gate is just going to be the NOT operation that's going to be applied to our qubit in that quantum register. So we index our quantum register by from 0 to if we have n qubits in that register, then we'll go 0 to n-1, like we do in Python. And of course, what this line of code is telling me is that apply the X gate to the first qubit in the quantum register. And we apply a barrier. So this barrier will separate the preparation part from the measurement step. And then we'll put a measure gate into our quantum circuit. And this is going to measure the qubit, and it's going to store the information in our classical register. So we can, of course, visualize our quantum circuit by using the draw function. So if we say qc.draw, and we specify the output to be MPL, this is for matplotlib, we get a very nice picture of our quantum circuit. So this tells us that we have the first qubit in our register. Well, there's only one qubit in the register. We apply the X gate to this qubit. The barrier separates the measurement step. And then we have the measurement gate, which is measuring this qubit, and it's going to store it in this classical bit here. So of course, we know from quantum mechanics and from quantum computing that the qubit, when measured, of course, it can be represented in some superposition. So of course, a qubit can be in any linear combination of the computational basis states, such that the amplitudes of each computational basis vector, their absolute value squared sum to 1, and that's going to conserve probability. But when we measure that qubit, we collapse the state, and the qubit can only take the state either 0 or 1. I will talk a bit more about this when we get to the Bloch sphere later on. But for now, we just want to measure the state of this qubit. And of course, if we started out in the state 0 and we apply the X gate, we expect to be in the state 1. So when we measure this qubit, we expect to see that it's always in the computational basis state 1. So to do that, we need to use the Chasm simulator. Now, the Chasm simulator, this is it's the quantum assembly language simulator, and this is going to simulate the circuit in the way it would be run on a quantum computer. So of course, what will happen is you would prepare your state, you would apply your gate, and you would repeat this process, say, n number of times, and you can get probabilities. So the Chasm simulator replicates this, but it's being simulated on a classical computer and not actually run on a quantum computer. So to use the Chasm simulator, we need to define what is called a backend. And in Quizkit, all the backends are actually obtained from the air package that's inside of Qiskit. So it's a submodule of Qiskit. And in this module air, you have access to a number of simulators, but we're just going to be using the Chasm simulator. So to actually get this backend, which is the Chasm simulator, we need to import air from Qiskit. And we say that the backend is equal to air.getBackend, and we specify that we want the Chasm simulator. And this is going to simulate the circuit, as I said, as if it's going to be run on a real quantum device. So the way we're going to use this is, of course, and I have a little explanation for how this Chasm simulator works, but the way we're going to use it is we're just going to create a job object, and we're going to say execute our quantum circuit with our specified backend, and the shots is going to be the number of times that we're going to sort of prepare our qubit, apply the gate, and then measure that. So we're going to measure 1,024 times. And because our qubit was initially in the state 0, we expect that after we apply the X gate, 100% of the time, we should get that our qubit is in the state 1. So what we'll do is after we execute the circuit, we say that res is just job.results. So we store the result object from our job in the variable res, and we just use the .getCounts function to get the counts. And we see that out of the 1,024 times we measured our qubit, we obtained that it was in the state 1. So this is just how we can run the simplest possible quantum circuit, just a simple NOT operation to our qubit. And as you can see, it's just a couple of lines of code. And we're simulating how it would be run on a real quantum computer as well. And of course, you can, when I put this notebook up, you can go through these explanations which explain each of these functions in a bit more detail. But as you can see, it's fairly easy to actually run quantum circuits on using Qiskit on both simulators and the real devices. But we'll talk about the real devices at a later stage. Before I move on, are there any questions? Okay, I don't think there are any questions, so I'm going to move on. Okay, so now that we've done the most basic circuit, we want to see, we always talk about this principle of superposition when we talk about quantum computing, quantum mechanics, and as I've said before, a qubit can be in any state 0 or 1 or a linear combination of them, such that the amplitudes, their absolute value squared sums to 1 to conserve probability. And so can we construct some quantum circuits such that when we measure our qubit for a certain number of shots, we see that it's roughly in 0 for half the time and 1 for the other half of the time, so that we can see the superposition in action. Of course, it's the same process. So we go with quantum registers, classical registers with just one qubit and one classical bit in it. and we construct our quantum circuit object again. But now we need a special gate that we would use. And as I said, gates are just unitary operations that you apply to the state vector of your qubit, which transforms that state into a new state. So the gate that we're going to use is just going to be the Hadamard gate. And this Hadamard gate is going to put our qubit in a superposition of roughly half and half. So if you made as many shots, infinitely many shots, you'd get that the qubit was half the time in 0 and half the time in 1. So we apply this Hadamard gate to our qubit, which is in the state 0 initially, and we put our barrier in, and then we measure. So this is what the quantum circuit will look like. It's just a Hadamard gate applied to a qubit in the state 0, and we measure. So we execute the job in the same way using the same Chasm Simulator backend, and we also specify the shots again at 1024. So we expect that if we were doing infinitely many shots, you'd get half and half being in 0 and 1. But because we have a finite number of shots, you're not going to get exactly half, but you should get roughly close to around 512. So after we actually execute this job and we get the counts, we see that about 500 times we measured the qubit to be in the state 0, and about 524 times we measured it to be in the state 1. These would get closer and closer to 512 if we increase the shots. But as you can see, the qubit is half the time in state 0 and half the time in state 1. And this shows that we've created a superposition by applying this Hadamard gate to the single qubit. So sometimes we don't want to look at the counts, we want to visualize the results. So what we can do is we can use some of the tools that are built into Qiskit to actually visualize these counts. And of course, if you have more and more qubits, it becomes more useful to do histograms than just reading off the list of counts that are in a Python dictionary. So we're going to use the plot histogram function, which is going to allow us to actually plot the counts that we obtained. So okay, it's the dark mode on my editor, but if you can see here, we have the probability of obtaining the state 0 at being about 0.488 and about 0.512 for obtaining the state 1. So this actually, you feed in your counts into this function and it produces a very nice histogram for you. Okay, now it's important to talk about another simulator. And the other simulator I'm going to be talking about is going to be the state vector simulator. So at this point, maybe I'll introduce a little bit of notation, or just some basics about the states of single qubits. And basically, the state of a single qubit is a vector in a complex Hilbert space. And if you don't know, Hilbert space is a complete inner product space. Inner product complex vector space, I should say. And quantum states are just unit vectors in the Hilbert space. So for example, if you have a state of a single qubit, then it just comes from a Hilbert space that's isomorphic to the complex number squared, for example. And of course, for a single qubit, our arbitrary state can always be written as a linear combination of just the two basis states 0 and 1. And if we express it as a vector, this is what it will look like. Of course, A and B are both complex numbers. And of course, as I said before, we require that the absolute value squared of each amplitude come to 1. This is to conserve probability. These values also have importance in the sense that the absolute value squared of A is the probability of measuring the state 0, and the absolute value squared of B is going to be the probability of measuring the state 1. So Quizkit actually has a simulator that when you construct a quantum circuit, it will output for you not a set of counts for how many times they measured 0 or 1, but it will output for you exactly the state vector that describes the state of your qubit after you've applied all of the operations, or rather I should say the state of your system of qubits after you've applied the gates in your circuit. So I'm going to show you how to use this the state vector simulator to output the state vector that describes our single qubit. So of course, now we don't need a classical register because we're not going to measure the qubit and then store the information in a a classical bit. We're just going to simulate the state vector that comes after we apply all the gates in our circuit. So we don't need a classical register. We just need a quantum register. And in the quantum circuit object, we're just going to have our quantum register. And of course, we want to have a quantum circuit that's going to create this minus state. And this minus state is just a superposition of state 0 and 1. But as you can see, we have a minus sign in front of amplitude of the state 1. So this is what our state vector looks like here. And we want to basically construct this quantum state. So of course, we know that when we initialize a quantum register, all the qubits are in the state 0. So to construct this minus state, we must first apply the X gate to our qubit and then the Hadamard gate. And you can do this with algebra and you'll see that this is exactly what you get. But of course, if we do it with Qiskit, we first apply our X gate to our qubit, the Hadamard gate to the qubit, and then we can draw it. This is what our circuit looks like. And now we need to change our backend because our backend was previously set to the Chasm Simulator. So now using the air module, we're just going to get the backend state vector simulator. And what we're going to do is we're going to execute our circuit with just the parameters being just the quantum circuit and the backend, and there being no need for the shots. Once we have the result object of this job, what we're going to do is we're going to say result.get state vector. So getting the state vector, we have the quantum circuit from which we want the state vector and the number of decimals we want it to. And then to print the vector, we get this output, it's the state vector. And it's precisely what we predicted the minus state to be, in our calculation. So this is how you can actually output the state vector of your circuit after you apply all the operations to your qubits in their initial state. Of course, in Python, you use the symbol J to represent a complex number. And you can see they don't have complex components in this vector. But if we want to use something like SymPy, which is another Python package, we can actually print out this vector in a more readable form by just using SymPy's pretty print function and their matrix operation to convert our state vector into a SymPy matrix. And then we use pretty print to print it out in a column vector like we always see it when we do linear algebra using LaTeX or something like that. Of course, we can easily interpret the state vector because we say that, if we take a 0.707 absolute value squared, it's half. And of course, the minus sign is not going to affect the probability. It's also a half. So we expect that half the time we're in the state 0 and half the time we're in the state 1. So that's just a very basic overview of how to use the functions in Qiskit to run some very basic quantum circuits. And it's fairly easy to just add more qubits and add more gates. But now that we've seen how to use these simulators in Qiskit, let's talk a little bit about the single qubit and the operations that we can do to the single qubit, namely the gates that we can apply to the single qubit. And we can also talk a little bit about the Bloch sphere, which is a way to visualize the state of a single qubit. Now, of course, in terms of single qubits, they're all represented by 2 by 1 column vectors. And these vectors come from this Hilbert space C squared. And remember, I said that these are unit vectors in the space, meaning that the norm or the length of this vector, I would rather say norm because that's the more appropriate term, of this vector is going to be 1. So, of course, for any single qubit state, we can always represent it in the computational basis using this parametrization. And this parametrization still holds all the properties of the single qubit that we're aware of, and that's that these amplitudes, their absolute value squared should sum to 1. And of course, you may be asking why do we only have? We said that A and B previously were both complex numbers, but this is real. But that's because there's also global phases in these quantum states. And as I said in previous mini schools, you might have learned about these ideas of global phases. And we can always factor out the global phase so that this is always going to be like a real number. And here we have we refer to this sometimes as the relative phase of the single qubit state. So what we've effectively done is we've said that any single qubit state can now be written as a parametrized vector like this, where we have two parameters, theta and phi, and these parameters can determine any single qubit quantum state. So the goal would now be that we want to see what are the operations we can apply to the single qubit state, namely all of the quantum gates that are available to us that we can apply to single qubits, and how they affect the state. So of course, if I'm just going to be using gates, they're just 2x2 matrices for single qubits, and I just show you 2x2 matrices being applied to vectors, that's going to be very boring. But luckily for single qubits, we have a very nice visualization, which is the Bloch sphere. And the Bloch sphere just allows us to take the single qubit state that you see here, and it will allow us to actually visualize it on a 3D sphere. So we have that single qubit quantum states are going to be represented as unit vectors in a 3-dimensional real space. And there is some more, I would say, advanced ideas of how you end up with getting from a 2-dimensional complex vector to a 3-dimensional real vector. I'm not going to go into detail about that here, but you can find more information about this in the resources that I've shown you, and maybe if you have a question, you can ask me after the lecture. But for now, we just have to use this visualization to see how the gates that we use on a single qubit actually shift the block, the vector, or the 3-dimensional vector, and how do they rotate it around that Bloch sphere. Okay, I just need to flip this sign in these inequalities here. This is a typo here, but I'll flip that before I upload this to the NITheCS website. So what we've seen is that, and there's something very interesting that you can take away from this relationship between the state of a qubit and a 3-dimensional real vector, and that's that these unitary transformations that we will apply to the state vector are just going to rotate the 3-dimensional vector, which we'll call the Bloch vector, which describes our quantum state on a 3-dimensional unit sphere. And that's something that's very important, is that every time we apply a gate to this state of the single qubit, all we're doing is we're rotating the corresponding Bloch vector based on the action of that gate. And as I will show you, I'll also talk about the types of rotations and the angles, about the amount at which the rotation is performed on the Bloch vector. Of course, it's important to note that because the Bloch vector is a vector in 3-dimensional space, it can always be parametrized in spherical polar coordinates, of course, with there being no radial component because it's always just one. And we see the relationship between the Bloch vector and the single qubit state is just given by the expectation values of the Pauli matrices. So of course, if we take this state psi and we compute the expectation value of sigma x with respect to that state psi, we actually get the first component of the Bloch vector. Similarly for sigma y and sigma z. As you can see here, I actually left you with some reminder of what the expectation value is and how to calculate it. Of course, what we're going to be doing is in the next section, plotting the Bloch vectors using Qiskit, is we're going to construct initial states of our qubits, and we're going to measure these expectation values, and we're going to plot that Bloch vector on a Bloch sphere using Qiskit. So the idea is we're going to see what some states of the qubit look like on the Bloch sphere, and then what happens when we apply gates to those states and see how the Bloch vector is rotated. But we're going to be using these formulae to actually calculate the Bloch vector each time for the single qubit state. So let's actually start. Before we can actually plot the Bloch vector, we need to import the plot Bloch vector function from Qiskit. And the first example we're going to be using is just, let's plot the state 0 on the Bloch vector, and let's see what that looks like. So the plot Bloch vector function can use spherical coordinates to plot the Bloch vector. So the way in which we can go about doing that is we see that if we were to compute the Bloch vector for just the state 0, what we see is that here, theta actually will need to correspond to the value 0. And to do that, if theta corresponds to the value 0, you can just plug it into this formula here, and you'll actually get that we need this block vector, which corresponds to the state 0. And in this case, of course, because we're using the spherical coordinates, we know that for theta being 0 and with r being 1, we can plot the block vector very easily. So we feed in our vector in terms of spherical coordinates, and we specify that we are using spherical coordinates to Qiskit, and it actually plots the block vector. So we know that for single qubits, when you have, if you want to visualize just the state 0 on a 3-dimensional unit sphere, the vector that's along the z-axis pointing upwards corresponds to the state 0. Now, we can also use Cartesian coordinates to plot the block vector. And if we do that in Cartesian coordinates, of course, the block vector would look like this. It'll just be 0, 0, and 1, where each of these corresponds to the expectation values with respect to each of the Pauli matrices. And we get the same block sphere that corresponds to with the block vector is pointing along the positive z-axis. So the next example would be to actually just plot the state that we created in the previous notebook, which is just the qubit being in the state 0 half the time and being in the state 1 half the time. So for this state, of course, we get that theta is pi over 2 and phi is actually 0. So if we want to do this with the coordinate, the spherical coordinates, what we're going to end up with is that r is always going to be 1 because we're always using unit vectors. And we just put in theta as being pi over 2 and phi as being 0. And we see that that points along the positive x-axis. So the plus state actually points along the positive x-axis, which is here. And if you were to do this with the Cartesian coordinates, what we'll get is that the first component of the block vector is just going to be 1 and the rest is 0. And this is very important. And the reason we have this, and this is because the state plus is actually the normalized eigenstates, one of the eigenstates of the sigma x matrix or the Pauli x matrix. And this is the eigenstate that corresponds to the eigenvalue plus 1. So that's why in this block vector, when you compute the expectation value with respect to the plus state of sigma x, you get 1, and you get 0 for the other two components. So there's a little exercise here, and that would be for you to actually use this the state 1 and the state minus, and then plot it on using the block vector function using Qiskit. And I ask you to do it both with spherical and Cartesian coordinates. So the idea would be to just follow the logic above here and try to do the same thing, but for these two states. So if you're doing, for example, using the spherical coordinates, we know that r is always going to be 1, but you need to figure out what are the values of theta and phi. Then only you could properly plot these state vectors on the block sphere. But if you're using Cartesian coordinates, then you can use the formula that I've given above for the state vector, the block vector, to compute in terms of the expectation value. And you can actually get your vector in Cartesian coordinates and feed that into the block vector function. So this is just going to be an exercise that you can look at. But of course, I'll give you a hint. And just as the plus state was one of the eigenstates of the Pauli X matrix that corresponded to the eigenvalue plus 1, the minus state is actually the eigen vector, eigenstate of the Pauli X matrix that corresponds to the eigenvalue -1. So of course, what you'd see is that the block vector you expect for the state minus should be pointing along the negative x direction, and the state 1 should point along the negative z direction. So I'll leave that for you to try on your own. And now that we're actually, now that we've seen how to plot vectors, block vectors on the block sphere, what we need to do is we need to look at all the gates that are used in Qiz that we can use for single qubits and how they affect a block vector. So the first thing we actually want to do is we import all of the known functions that we were using: quantum circuit, quantum register, classical register, execute, and the air backend. Of course, we're not going to use classical register in this part, but oftentimes I import all of these things just so that if we need to use it, it's available to us. And then we write a function that extracts the Cartesian coordinates for the Bloch sphere from a state vector. So this function, when you input a state vector, what you're going to get is it's going to output the x, y, and z components of your Bloch vector. And it does it by actually computing the expectation values of the individual Pauli matrices with respect to the state vector that you input. And it stores it in a list, and it returns it to you. So let's just have a look at, what does the Bloch vector look like if we apply the X gate, which you've seen previously, to this qubit in the state 0. So we know how to construct a circuit that just applies the X gate to our qubit, and this is what it looks like. We simulate it using the state vector simulator, so that the output that we get is actually a state vector. And of course, you can see I'm storing it in this variable state vector. And when I want to plot the Bloch vector, I just say plot Bloch vector, extract Bloch vector, which is the function that we've written above, and we feed in the state vector that we obtained from simulating the circuit that we've created with the state vector simulator, and we specify that our coordinate type is Cartesian. And as we can see, the Bloch vector that's been placed here has now been rotated so that it points along the negative z-axis. So we sort of flipped the Bloch vector, and this is why you'd see in quantum computing they refer to the X gate as the bit flip operation, because it flips the bit from the pointing along the 0, the positive z-axis, to the negative z-axis corresponding to the state 1. So of course, the X gate induces a pi rotation around X. So there's the axis here, and then a pi rotation would be this way, and you'd get to the state 1. So now let's look at what the Y gate does. So the Pauli Y matrix, what does that do to the state plus? Now, of course, the reason I'm applying it to the state plus is because you won't really see how it rotates the Bloch vector if I apply it to 0. So we need to create a circuit that actually first creates the plus state as our initial state, and then we apply the Y gate. So we know how to create a quantum circuit by now with a quantum register. So first, to create the plus state, because we know our qubits are in the state 0, we're going to apply the Hadamard gate to that, to the qubit being in the state 0, and then apply the Y gate after the Hadamard gate. That's the circuit you see here. And once you've actually done that, we're going to use the state vector simulator to actually get the state vector after applying these two gates. And we're going to extract the Bloch vector from our state, and we're going to plot it. And we actually see that it points along the negative x-axis. Now, we must remember that the plus state points along the positive x-axis. So how did the Y gate actually rotate this vector? Well, the Y gate was actually a pi rotation around Y. So that's actually how we ended up here. So if we go a pi rotation around Y, we go up and we come there. So lastly, we want to see what the action of the Z gate looks like on the qubit in the 0 state. Now, let me just quickly change this. So the Z gate is defined like that, and all we're going to do is we're just going to okay, sorry, this should also be plus here. So the way we're going to do that is we'll first construct our plus state and then apply the Z state, the same as we've done, the Z gate, the same as we've done above. And the code is the same. We're simulating the output of the same circuit. And what we end up with is when we plot the Bloch vector, we also, pointing along the negative x-axis, and we started along the positive x-axis, but the Z gate is going to be a pi rotation around Z. So in this case, it's going to go that way. It's going to rotate here. With the Y gate, it rotated that way. So this is how these gates rotate the state of the qubit on the Bloch sphere. So now I just left a couple of exercises that will be interesting to attempt, and that will be that, can you show the action of the Hadamard gate on the state 0 and describe the action of this gate in terms of a rotation around X and Y. I also say that, I want you to show the action of the S and the T gates, which are available in Qiskit. And of course, how you would get them is you would just do qc.s or qc.t and apply it to the corresponding qubit in your register. And I want to see what is the action of these gates on the plus state, and also describe the action of these gates in terms of rotations around Z. And you can put your code in these cells when you're trying this tutorial for yourself. And the last thing I want to show you is that usually with these single qubit operations, we can oftentimes simplify them. So if we have, for example, HXH, we can obviously write that as just Z. And the way we're going to show this is we're going to show the action of HXH on plus and the action of Z on plus, and show that they're the same thing. And by now you should know how to create a quantum circuit using Qiskit and add the operations. So first we put our qubit in the state plus, and then we apply the gates HXH. We run the circuit as we've done before, and we plot the Bloch vector, and we see that it's pointing along the negative X direction. And of course, if we do the same thing, but with just H and then we apply Z, which is the same as HXH, we run the circuit as we've done before, and we see we get the same output. So that's just something I wanted to show you, that you might be able to actually simplify your quantum circuits by using or making use of these special properties. For example, the fact that Z is just HXH. And this is just something interesting I thought I'll show you. And the way we verify this is by looking at the action of these gates on some initial state and then plotting the Bloch vector. And if the Bloch vectors are the same, then what we've ended up with is that these two sort of operations are actually doing the same thing to our qubit. Okay, and then the last thing I've left here is for you to just show that HZH is just equal to X. And for those of you in the audience that do any algebra, you'll see that this is very, very easy to show, because the Hadamard Gate squared is actually identity. So it's very easy to actually show this just using some algebra, but I would prefer if you do it this long way, just to get the use or get the hang of how these functions work, and using the Bloch vector to visualize the states of your single qubit. Yeah, so I will actually put up these tutorials. I think Prof said on the NITheCS website, and from there you'll be able to access it, download it, and then add your own code and play around with these functions, and maybe just have some fun plotting different Bloch vectors. And maybe you can try using some other gates to get Bloch vectors that aren't necessarily pointing along any of the axes, but maybe an arbitrary Bloch vector. And maybe during the next lecture, we can talk about how to actually move that Bloch vector to an arbitrary point on the sphere using a general unitary transformation. But for now, that's all I want to say about single qubits and Qiskit. In next week, I would like to actually go through 2 qubit operations. So how to use 2 qubit operations in Qiskit, and maybe n number of qubits, so 3, 4, 5. And maybe if we have some time next week, we go through a very simple algorithm that uses multiple qubits to actually do some type of computation. And then we'll go on from there. And then I'm hoping to, in the 3rd week, talk a little bit about quantum teleportation and Grover's algorithm. And in the last lecture, I would actually like to discuss something that's a bit more modern, and show you a distance-based classifier from quantum machine learning, and how we can implement that on Qiskit. So that's going to be all from me. If you have any questions, feel free to ask them now. Thank you.
Yeah, thank you very much, Jan, for this very nice introduction to Qiskit, and for showing us some very nice examples.